Hey everyone, welcome to the Tech Tuesdays webinar on MDM Fuzzy Match Deep Dive. I'm Brinda Anil and I'll be hosting today's webinar. In this webinar, we'll have a look at the internals of how MDM processes fuzzy match jobs with an eye towards performance. The presenter for this webinar is Augustine Chan, who is a member of the MDM ACE team and is currently working on enhancing the fuzzy match engine in MDM. Before we start off, here are some housekeeping tips. Today's webinar is scheduled for 1 hour, which includes a 45 minutes webcast. At the end of the presentation, we will roll over to live for 15 minutes to answer your questions. The session will be muted so that the presenter will be able to present without any interruptions. Your questions can be submitted through the Q&A section and we will be addressing them to the end of the presentation. The webinars will be recorded and will be available in the Informatica Support YouTube channel and Success Portal. The link also will be emailed to you. Please set aside some time to complete the post-webinar survey and provide your feedback and suggestions for upcoming topics for the Tech Tuesdays webinars. The Tech Tuesdays webinars is a webinar series introduced within the Success Portal. The Informatica Success Portal is a micro-learning platform that offers free and unlimited learning to all registered users. The Success Portal lists your success offerings, your customer success manager information, bookings available in the Ask an Expert session, and customized recommendations and content. Our new intelligent virtual assistant Diana is available in the Success Portal for all our cloud customers. Over to you, Augustine. Thank you.
Thanks for the introduction, Brinda. We've got a ton of slides, so let's get started. We'll be talking about these two records and the journey that they take through the MDM fuzzy match process. Just some background on the matching that we do, on what we use for matching. We use something called SSA name 3 under the covers, and it uses a combination of fuzzy keys and ranges. And we'll go more into this later on. But just to take the company name as an example, Automotion Corporation goes through some processing. We get rid of the corporation noise word, and then we do phonetic stabilization to automaton, and then finally name 3 kicks in and generates some keys for us. And these are based on sort of the combinations and permutations available from auto and motion. Okay, and to configure the key width, also known as key level in name 3, you would go to the match columns panel in the hub console for your base object. So our example is using extended key width and organization key type. And this is mapped to a column called display name. So those of you familiar with MDM sample will be familiar with this. And the display name resides in our party table in the root match path. So the topmost table in our configuration. So how these keys look like in the Workbench, you'll notice that the Workbench, which ships with the resource kit, we're doing the same thing. We're calling we have controls for the field, organization name, key level extended, and the organization name that we're passing and generating keys on is Automotion. So we get 4 keys here and 4 keys for Automation Corporation as well, because corporation is a noise word. And how it looks in our strip. So remember, we store our keys in this table called the strip. And so for these 2 row IDs, we have the same 4 keys, and associated with these 4 keys is a column called SSA data, which contains all of the denormalized data from the other associated match fields configured for this base object. So if we could slide this screen to the right, you would see child addresses, child phone numbers, and other child data if they were available for that record. Search ranges. So search ranges are used to find the candidates for matching, right? So in essence, we're trying to figure out what are our match pairs, and our search ranges help us find the file candidates, what we call the file candidates. It's a pair of 8-character strings and can be thought of as the fuzziness around a key. So in SQL terms, we're basically saying, give me all the records with keys between these two strings, which is the range. So these ranges are not persisted in any table. You won't find them anywhere. They're generated at runtime while we're doing matching. Now you can see ranges in our cleanse log from our ThreadMonitor and match summary. And so if we want to configure how many ranges or how extensive our ranges are, that's done from the Ruleset area, right? So this is a typical search level. This Ruleset is typical. And I've circled these two rules in red here, these two fuzzy rules in red here. It's because the search level only applies to the fuzzy rules in your rule set, right? Exact rules are processed in a different phase using database operations and SQL and temporary tables. And so they don't use ranges for candidate selection. Only the fuzzy rules use the ranges for for candidate selection. So these are how the ranges look in the Workbench. So you'll still get the same 6 ranges for 2 records because because corporation is noise or skip. And let's take a look at Automotion Corporation, the ranges and how we generate them under the cover. So for typical search level, we generate 6 ranges, and it's based on sort of the permutations as well as the secondary name variations for the auto portion of Automotion. Okay, and so that's how we get 6 ranges. So if we were to query our strip again and find the number of candidates for each of these ranges, this is what we would see. So the numbers in red are the number of records in the strip with keys within the specific ranges shown. Okay, so 5 candidates, 4 candidates, and these other ranges don't bring back any candidates at all. And if we look in the cleanse log in our RangerWorker summary, here's where we show the same metrics again, 5, 4, 0, 0, 0. So it's all this. It's using the same metrics that you would get if you were to manually query the database itself. Match job internal. So just from an overall perspective, when a request comes in from the outside, the server ear is listening on port 8080. Well, this is for JBoss, and that's configurable. Port 8080 on the cleanse URL. And once a request is received, if it's of type new match, we know to route it to the cleanse ear and perform fuzzy matching. And so it starts off with this class called match.java. Match.java will end up opening in SSA Session and opening a connection to the database. The match process does. And opening an SSA Session is done through this jar called the info MDM external SSAN3.jar. So this is an interface jar. We go through the Java native interface to communicate with the library, the shared libraries, the DLLs for name 3. And the other thing that we load is the population file. So I'll be using the demo.ysp population file, which contains the other, the edit list and secondary name variations and other rules for that language. And of course, we will be talking to the ORS, which contains our base object and our strip table. We interact mostly with the strip table. We interact with the base object table to flip some indicators to signify that we performed matching on them for the most part, but we mostly interact with the strip table during matching. If we set this cleanse property to 1, distributed match, then we know to distribute the fuzzy match job to the registered process servers. Match job execution. So now once we start our fuzzy job, we kick off things first with tokenization to see if there's any dirty records that we need to keep track of. Then we do fuzzy matching itself and see if there's any fuzzy rules in the rule set. If there are fuzzy rules in the rule set, we'll kick off this parent process called Ranger. Ranger is the process that kicks off all the other threads involved in fuzzy matching. Once those are done, we then call exact matching on any exact rules in the rule set, and then end. So one of the questions that we get, or one of the performance questions we get, is my match job is running long. What's going on? And a lot of times we'll start immediately looking into the match portion of a job. But that's a mistake. You really have to look at all of the portions of a match job before you start looking at fuzzy. I've seen cases where the majority of the time in a match job was done in tokenization because these ratios, the strip CTAS limits and ratios, were not configured properly. Meaning during an incremental load, a daily incremental, a complete rebuild of the strip was done against several hundred million rows in the strip, which just blew out their incremental match job window. So just that's what this warning is all about. So just be aware of these limits and settings and before honing in on the fuzzy match portion of a job if you notice slow performance. So once we're in the matching process, the way to think about the matching process is it is sort of like a pipe, right? And we're not looking at all of the records in the match batch to begin with. We are processing portions of the batch at any given point in time, and we're using a series of blocking queues of modest size. So this is a producer-consumer model, right? We have a series of producers and consumers that are reading data from the database. So we're reading the strip data and then generating search ranges for all of the records in our batch, and then feeding those ranges to this process called the sort manager, which creates our units of work called RangerNodes. So the way to think about the match process is it's sort of like a pipe, right? And the pipe is, you can make the pipe wider by giving it more threads, right? But the data coming through the pipe can sometimes have chunks, which we call match hotspots. And those chunks can be hard to deal with. There are ways to deal with them, and I'll go into how to deal with them later on in the presentation. And those chunks can serve to slow down the match process by sort of clogging up the pipe, right? And so let's go to the next portion. So we've read data from the strip to generate ranges, and we've sort of packaged these ranges into RangerNodes. And this is what the producer step is doing. It's reading the raw SSA data, and it's just preparing it and reading rows and putting them in memory in the form of this block in the blocking queue, this internal blocking queue. And then once it's there, we're reading key data, and it's reading, this is what it looks like in the log, right? We're starting the producer, we're reading data from the strip, and it's saying we finished reading those 2 records in our batch. Once we've read those 2 records, then our Ranger workers will generate the ranges, and of course we generate 12. So if you remember, each record had 6 ranges, so if there's 2 records, we generate 12. Here's a note on just a search level in the log. Just look at this portion. Look for this message to actually figure out the search level. Don't look at this message over here at the top. And so we generate our ranges. We have 12 total ranges, and then we sort of sort them in alphabetical order, and then we assign records from the batch into the Ranger nodes with those ranges, right? And this is the size of each Ranger node is determined by two things. One is the number of candidates that are brought back by the range, which is sort of hard to know at the beginning when we create this Ranger node. And the other part of it is the number of search records for that range. The number of search records is controlled by this property called max records per Ranger node. So on default, we can hold up to 3,000 records per Ranger node. In our batch, we only have 2 records in our batch. So each of our 6 ranges has one Ranger node, and it has 2 records each. If you have more than 3,000 records that generate that particular range, we'll just create another Ranger node for those extra records. Packaging the Ranger nodes. So this is what packaging the Ranger nodes looks like. So we try to distribute from memory these 12 ranges, and we generate 6 Ranger nodes for them. And now, remember what I told you, that this is sort of a producer-consumer model, and at any point, we're only looking at a small piece of the job at any point in time. For large batch jobs or for normal-sized batch jobs, this sort manager won't actually finish until you're almost done matching. Because you remember, the slowest part of our matching process is the match threads. So they tend to block all of the upstream processes from completing. And so the sort manager is only going to be able to really finish near the end when the range, near the end of the job, because there's not a lot of capacity between the sort manager, between the queue that's between the sort manager and the Ranger workers. And so in the log again, we've got range generation and sorting and packaging, just to illustrate the differences of how it looks like in the log. Our Ranger workers generate ranges, and our sorting is done by the range sorter. Or within the range sorter, there's this class called the sort manager that does our creation of our units of work called RangerNodes. So further down from the sort manager is our Ranger worker that actually performs matching. So it takes Ranger nodes off the primary work queue, and any matches found, we generate match rows for them and feed them to the match gatherer, which is in charge of deduplicating these match rows, persisting them to a temporary file for loading into the match table. Okay, so now we're getting into the nitty-gritty of what it looks like when we're doing our matching. So if you remember, I talked about these units of work called Ranger nodes. They contain up to 3,000 search records from the batch, right? And that's in this thing called the match node array. So there's 3,000, up to 3,000 elements. We only have 2 elements in our batch. And this range is this is the range that's assigned to this Ranger node. And within the match node array, the elements within the match node array, it contains the data from the strip for that row, right? So this is the SSA data column. Okay, so this is just basically getting it ready for matching. When we are processing a Ranger node, what we do under the covers is we open a connection to the database, right, to bring back our file candidates from the range. And then as we were bringing back file candidates from the range, we're comparing them one by one against all of the records in our match node array. So we've got 2 records in this Ranger node, for example, with, UIV, blah, 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 to UIV, blah, blah, blah. This range brings back these 5 candidates, okay? So what we do is we open a result set against this range and bring back our file candidates one by one. So we bring back the first one, row ID 1042, and we compare that to 991 and 966. Only then do we go to the next file candidate in our range, and then we compare it to our match node array, the elements in our match node array, and so on and so forth. So all of the RangerWorker threads are doing this concurrently, and it's quite memory efficient because we're not loading the entire result set and into memory, right? We're just opening the result set, querying it, and scrolling through it one by one. And so that's why our match process is not really sensitive to the data volumes. It's really sensitive in terms of memory. It's really just, it's tied to the number of threads that we use for processing. If you make your match node array larger, then of course each thread will consume more memory because it has to keep more search records in memory. Okay. So the way to think about how we do our processing is, we have to think about what's the most efficient way to process a match for this rule set, right? So this rule set contains a mix of exact and fuzzy rules, so we'll register that. And then for our fuzzy rules, actually for all of our rules, we will figure out something called the total nodes and the actual nodes. And the node is basically either an exact match field or an SSA purpose, okay? And what we do is we distinct down all of the total nodes into the distinct nodes that need to be evaluated for all the rules in the rule set. So we've got 12 total fields and purposes, and they really equate to just 5 nodes. Or 5 fields or 5 match calls, 5 distinct match calls that need to be evaluated. So, as an example, this match column called EX Telecom is shared between fuzzy rule 2 and fuzzy rule 3. So we can do some optimizations around that. And I'll go into those optimizations in the next slide. So for fuzzy match pair evaluation, what we do is we figure out whether a rule set node is either an exact match field or an SSA purpose. And then we figure out the distinct set of rule set nodes across all the rules. We evaluate all of the fuzzy rules in order for a given match pair. And for an individual rule, fuzzy rule, we evaluate the exact nodes first. So this is why we always recommend, hey, you know what, you should use exact match fields where you can, because they get evaluated first. And if a match pair fails their evaluation on that exact field, we don't have to perform the SSA purpose call. The fuzzy call is skipped. And the other interesting optimization do is if any node fails, all the rules that use that node are also removed from evaluation. So if you recall, EX Telecom was shared in rule 2 and 3. But since we're checking EX Telecom in rule 2, if it fails for that pair, then we can immediately eliminate rule 3 as well for that pair, right? And if any node evaluates as true, so if an exact match field or a purpose call evaluates as a positive match, then we store this result so that we don't have to redo that evaluation again. And this is especially useful for those expensive calls to SSA, right? So for those expensive SSA purpose evaluations, if they evaluate as true, we reuse that if that same purpose is done in another rule in the rule set. And so just keep in mind, any of the exact rules are processed in a later phase in the database. They're not done during the fuzzy phase, right? So our match record. So this is what an internal match record looks like, right? Basically, we parse out all the data from that SSA data column, and then we figure out the match fields for them, and then we figure out what those we tie up all those match fields together to our parent party object. So our party object has been, and its child data has sort of been denormalized into this record, right? And row ID 991 is a bit more interesting because it contains multiple address lines and multiple phone numbers, okay? Now, how do we handle multiple fields or multiple, let's say we have 2 records with multiple phone numbers. So exact processing is done in the app server side, right? Within fuzzy rules. So we just basically do a Java string region matches, which is basically a string comparison, to figure out whether there can be a common phone number found between these 2 records, right? And so what we'll do is we'll try all our combinations, we'll iterate through them until we can find a match. If we can find a match early, we'll stop. If we can't find a match at all, we have to go through all combinations. And so that's why non-matches can be expensive, because we have to go through we have to iterate through all the child combinations before we can say that there is no common phone number, for example. Okay, and so that's for exact fields. Now, for purpose calls, let's say there's multiple addresses that we want to handle as part of a fuzzy address evaluation. So what we do is we rely on SSA for that. So first of all, what we do is we figure out and create this thing called a layout to specify, hey, given this string, this record with this SSA data, we're going to send you this string, SSA, and we're going to tell you to look at specific portions of this string for the specific match fields that are required for the purpose evaluation. So in this case, I'm just highlighting here are all the addresses. The 41740 Broadways from row ID 991 are sort of specified in the layout for SSA in this manner. And so when we call SSA, which contains multiple child data, we only do one SSA call, and we let SSA sort of handle the under the covers enumerations and combinations and matching evaluations that need to be done, right? So under the covers, SSA will figure out, can I find a common address given these 2 sets of addresses? So it'll iterate in this manner. And if we can find a match early, we'll stop. Otherwise, we have to go through all of the combinations before we can say that there is no match. And so that's what it looks like from the workbench, right? We've got several address part 1s on both records, and we do find a 100% match because we're looking for one common address across both of the records. So subtype matching gets all sorts of questions and confusion around subtype matching. So if you recall, when we look at a record, on default, we treat all of the child information together as sort of one set, okay? Subtypes, however, is saying, I want you to not treat all of the child together in one set. I want you to group them into these logical groupings based on a column, which we will tag and specify as being a match subtype. Okay, so the match subtype is typically in a relationship table, and then the associated fields tied to that type are typically on the other side of that relationship table. So we've got a party, an address row with an address type field, which is tagged as the subtype, and then we've got address, which contain our address lines. So the address type actually has 2 different types, ship and bill. So what we do in subtype matching is we break up the record into 2 different layouts, a shipping layout, which only contains records tied to the shipping type, and a billing layout, which is tied to records tied to the billing type. And so this obviously shoots up the number of SSA calls that we need to do, because we need to do this for both sides, right? We need to do it for both the search record and the file record. We need to figure out the sort of the sub layouts for each and enumerate through all of the possibilities. And so that's why subtype matching kills performance, and we try to tell you to avoid subtype matching if you can. Now, if you have flexibility, you can work around subtype matching using something called a filtered match path. So I can say, you know what, instead of a generic match path, that is what this is, I'm going to create filtered match paths for each type with the associated address relationships and child data, and create rule sets or create rules using those specific match fields that are tied to those filtered match paths. And so doing things that way, you can improve performance. Okay. So that's just a pointer for you guys. Match batch distribution. So when we have multiple process servers and we want to distribute the work across multiple process servers, we need to sort of first figure out what process servers I have, and then I have to figure out the relative power among my process servers. And the way we do that is we figure out, we read the CPU rating and we multiply it by the number of cleanse threads to come up with some factor. And this is done for all of our process servers to figure out how powerful they are in relation to each other. And depending on that rating or that power rating, we figure out what portion of this 1,000 work range can be assigned to an individual process server. So I have two process servers of equal strength, then they each get equal portions of the work, of what we call the work range, which is used for distribution in fuzzy matching. And so once we have that established, at runtime, what we do is we apply a hash code and mod it by 1,000 to the concatenated range. So this is actually 16 characters. This is the search range. And we come up with a value that's been scaled to 1,000. We take the absolute value if it goes negative. And based on that, we decide what process server should process it. Now, keep in mind, this is not done by a master process, right? This is done by every process server concurrently that is performing the match job. Each process server is generating all of the ranges, but then each process server is applying this hash evaluation to determine whether that range should be packaged into a RangerNode and whether we should perform matching on it, right? And so that's sort of the method that we've taken for distribution. So we don't guarantee 100% equal distribution of ranges. It's based on this this hashing we do. Okay, understanding the cleanse log. So one thing that sort of can be challenging to figure out is what version of the name3 library I'm actually using and what version population I'm using. And so for that, we have an info level log at the beginning of my match job, which is, so this is Ranger, right? I will open up in a session and SSA comes back with a response message that's broken up into two parts. The first part is the version of the SSA library, and the second portion in blue is the version of the population, right? Under the covers, we go through an interface jar, which is embedded in our ear files. And so that can only be known by sort of opening up our ear files and looking for the SSAN jar, okay? And so, you know, if support is asking you for versions, this is the way to do it. ThreadMonitor. Okay, so while we're doing matching, we have this process called the ThreadMonitor, which pings every minute and asks of our match threads, hey, what are you guys doing and how are things going so far? So the first part of the ThreadMonitor, which starts with a T, is asking, how are things going so far with these specific counters, right? So TCAN is the total number of candidates, database candidates have been read by this thread so far, and so on. I'll let you read those. And cur and comps per range is talking about, hey, what are you doing right now? It's asking this, what are you doing right now? So right now, this thread is evaluating this file candidate. This is the row ID of the candidate that's being evaluated right now. This is the range of the Ranger node that we're processing right now. Comps per range is saying, this is the total number of comparisons I've done for this Ranger node so far. Okay, so that's the way to read this ThreadMonitor. And this ThreadMonitor can be used to find hotspots. So if you notice that through many subsequent polls of the ThreadMonitor, if you notice that this range is not moving, but your SSA comparisons are shooting up, then you know you've run into a hotspot. But otherwise, yeah, that's sort of the best way to use it, I think. And so at the end of your job, each thread, RangerWorker will come up with a summary of what it's done. And so the first part of that summary it shows is, here are the ranges that had the most database file candidates that had to be read from the strip table. Okay. And the second part of that is similar, but not quite the same. It's saying, what are my ranges that had the most comparisons that I had to do? And we get the number of comparisons by multiplying the number of search records in that RangerNodes range by the number of file records in that range. So, you know, usually in a normal job, you may see a lot of queues with 3,000 here. And in a normal job, this DB can be a couple 100,000 or in millions or more. Okay, so the number of database candidates can get quite high in this. And the way to use these range comparison summaries that come up at the end is they could be used to pick a relevant DMAT, right? So if I chose a DMAT of 8 for this job, that says I would process this, which I would process range 1, but I would skip range 0. So for your jobs, you might see at the very end some outlier ranges that have comparison counts that are extremely sort of maybe 10 times higher than the next highest range in terms of comparisons. And those are candidate, and that's when you might consider to use a DMAT that's below those numbers. You would need to do profiling and to see whether those missing that range is acceptable to the business, and whether the records in those ranges would be sort of caught in other ranges. But that would be one way to use this summary at the end, is to try to pick a DMAT from it. So fuzzy match summary. So this was a summary for the batch that we ran. We had 2 records. We read 9 total records across all of our ranges or RangerNodes that were processed. We found we processed 14 candidates, and we performed 11 SSA purpose evaluations, and this number will go up if you use subtype matching. Ranges created is the number of search ranges that were generated by all my RangerWorkers and across all my process servers. Actually, this would be per process server, sorry. Ranges processed would be the number of RangerNodes processed by this process server, okay, and so on. And this is what the log looks like at the end of my job before the exact portion begins. So after my fuzzy portion ends and then gives that summary, we will start to process and check to see if there's any rules, exact rules. So we found one exact rule, and we say, okay, what are the columns, the exact columns for this rule? And based on that, I figure and determine out what are my MTIP views that I need to process the joins that I need to process those columns. So that's just what to look out for. Okay, improving performance. So I've only got one slide on this, but I hope it's good enough. So the best and easiest thing to do is just to use as many exact fields as possible where appropriate, okay? This helps us to eliminate as many SSA calls, and exact fields that are shared across many rules allows us to do early elimination of rules as we're doing the rule set evaluation for a given pair. Okay. Avoiding subtype match, I've talked about that before, and the reasons why that can shoot up the number of SSA comparisons. Adjusting your frequency table. So this is not done common enough, probably because we don't do enough education on this. But basically, you should ensure that the words in your data are recognized as common by SSA. Once they're recognized as common, SSA does special handling for those words in terms of keys and range generation. And so this is done using the population override manager, which is shipped with the resource kit. If you notice that in your matching you have a few straggling Ranger workers that take much longer to complete than others, then that signifies you have match hotspots. And so what you can consider doing is decreasing your max records per Ranger node from 3,000 to some smaller number to smooth out and improve the concurrency of the match threads. The other thing you can do is you can configure DMAT if match quality can be sacrificed. Decreasing max records per Ranger node will not decrease match quality. It will increase the database records read because those same file records have to be read in different threads because you're sort of breaking up the search records into multiple smaller chunks. And so yeah, and then analyze your RangerWorker summary top count. So please check for unusually large counts against a strip and see, and if the SSA data column shows that there's a lot of noise words associated to those keys, add those noise words with using POM, Population Override Manager. And so please, any population changes should be well tested in lower environments before promotion, and please, you can reach out to GCS for help as needed. And now we have time for Q&A. And so thank you. And if you guys have any questions, you can reach me at achan@informatica.com. Thank you.
Hi guys. We have a bunch of questions. Let's see what they are. My screen is refreshing now. Just a sec. Oh, well, I remember one of the there's a few questions that was asking about the SSA data column. So the SSA data column, actually, all the data in the strip is generated from a tokenization job. So I didn't really delve into that. But basically, in your base object, when you're configuring it, you're basically specifying, you know, how to find the match field data that's associated with that base object. So there's something called a match path, where you'll specify where, you know, child addresses might be coming from and phone numbers and so on. And so the tokenization job uses that information to denormalize the data and persist it into the strip during a tokenized job. So that's where the SSA data column. That's where the SSA data comes from. Okay. Okay, so Derek had an interesting question around, you know, child matching for SSA, so, or just multiple field matching for SSA, because it was a bit confusing because we think of SSA as being a fuzzy match, but I said on slide 37, let's see, is there a way to, how do we push this guy? Push to audience. No. Anyway, on slide 37, there's just basically that example that goes through and shows the address fields getting past SSA, and we stop early, right? Is this? Did that work? No, that's a subtype matching. Okay. Try pushing this one. Ah, yeah. And so we only stop early if we can find a 100% match, which oftentimes is a string match, but it doesn't have to be for a fuzzy, right? We'll stop early if we can find a 100% match. If we can't find a 100% match, we'll return sort of the highest match found, right? And that can be either above the accept threshold or not, but that's another matter. Okay. Okay, I've got a couple of questions Abalash. How to best handle a base object that contains both organizations and individuals. So we typically recommend using organization name for your key, and Anshul actually answered that. The one that was a little hard to deal with. Is the fuzzy match key defined at the BO level mandatory in all the fuzzy rules in a match rule set? Okay, so this is one of the confusing things. When we configure a key and a search level for a base object, and you might have many, many different rule sets against that base object, they're all going to be using the same key and all the same key. Now, the search level can be configured per rule set, but they won't. You can't assign a different key type per rule set. So if you have a rule set focused on addresses versus names, for example, they'll still be using the key that's been configured at the base object, which is going to probably, which can be either organization name or address or something else. Okay, so a little bit tricky there. But this is at a base object level, so you can have different rule sets per base object, right, and different keys per base object. So do we need to increase process servers with respect to match count? So remember, there is a relation, but it's not a direct relation to the match batch size, right? It's based on range and the ranges that are generated from your batch. So so in that respect, the search level has a very high impact on performance, right? Because the search level directly impacts how many Ranger nodes gets generated. So the range, so how many Ranger nodes has an influence on your time, but the content of the Ranger nodes has the biggest impact. So if you have Ranger nodes with, bringing back many, many candidates from the database because their search range is very wide, and maybe those pairs are passing all of your exact field calls. So they're passing the exact string evaluation for all your exact fields, and they're dropping down to SSA for fuzzy. So those are going to be very expensive. And so, more threads will help. And so it will help because you can have more parallelization in processing of your job. But you will have hotspots in most jobs. And so if you have hotspots, like I mentioned in the last slide, you can consider decreasing your max records per Ranger node, because your max records per Ranger node controls one aspect of the size, which is the number of elements in that match node array, right? So if you make it smaller, you can try breaking up those large Ranger nodes into smaller chunks, and you can try to get better parallelization that way. So, so it's really about threads, not necessarily process servers, but usually there's a correlation there. And so more questions around multiple match rules and how's the SSA data. So remember, the SSA data is tied to the match fields that are configured against the base object, and Harish answered that question. It's not tied to the rules per se or the rule sets. It's tied to the match fields configured for the base object. How does segment match work internally? Is it better compared to subtype? So segment match works internally very close to basically an exact string match. It is it's quicker than a subtype because it does not imply generating sub layouts and calling SSA multiple times. You can think of a segment match as basically a special, or just like it's just basically an exact match rule, but it's basically saying either all of the values within that segment are allowed, or more typically you might have a rule set that contains both, party, individual rules and organization rules, right? So in that sense, that's when our rule set optimization kicks in. So if we quickly, we'll quickly determine whether this match pair shares a party type, for example, let's say you have a segment match on party type, and if they both are both individuals, then the individual rules in the rule set are used, and the organization rules in your rule set are quickly eliminated because you know, it won't pass the organization evaluation for that segment, right? Okay, Derek's asking a tricky question. I won't answer that one. There are addresses like in Colombia that are based on numbers. Street 1, Street 11, Street 111, and are impossible to match them. How can you share a strategy that can help? Have to get back. Oh, Ansel answered you. Can't think of a great one there, but there's probably a good way. Yeah, similarity between subtype and segment. Yeah, segment is basically, we've answered that. Segment is very close to just a string match. Subtype implies adjusting the SSA layout and multiplying the number of SSA calls. Exact match, yes, it's case sensitive. Now, you know, yeah, and actually you'll have to distinguish exact match in the app server, which is exact match fields as part of fuzzy rules, versus exact match in exact only rules that are handled in the database, right? So exact only rules that are handled in the database, well, then that's really up to how the database handles joins and on column values, right? Okay, and this other Roberto is asking a question about a match job that results in a very large cluster and a super row ID that's tied to a quote-unquote super row ID that runs for 4 hours. So that's really match hotspots, right, Roberto? Basically, what's happening there to form that super cluster of 10K XREFs, we have to do sort of this Cartesian product of comparisons to sort of form that cluster, right? And so in that sense, what you're probably experiencing for that job is poor concurrency, because you might have a handful of ranges that have many, many SSA comparisons to complete them, and other ranges that are really quick. And so you'll have a large set of threads that are actually idle. And for that particular job, what I would do is I would look at the summaries, like I specified in the PowerPoints, and try to find the records that are tied to those search ranges in that cluster. And so that's a little tricky. You'll have to do some profiling against a strip to sort of work that back. But anyway, you can try decreasing your max records per Ranger node to attempt to break up that large range into smaller chunks, right? So that's one possible. Maybe instead of 3,000, you might try to say 500 or something similar. But take a look at that, your summary, your cleanse log summary. You can try opening a support case and looping me in, and then we can look at that more closely. If I have 1,000 records and the match batch size is 100, is it a good practice to process 100 records to undergo match merge? Or is it a good practice to process all 1,000? So I see people doing this. It is tied to how the Ranger nodes are organized, right? So when you play around with the match batch size, and when people try to make the match batch size smaller, what they're really doing is, by luck and happenstance, happening on specific boundaries to sort of, make specific ranges smaller, right? So you might be lucky for a particular boundary that might happen to chop a large Ranger node in half, just because maybe some of the search records are in one portion of the batch versus a later portion of the batch by making that match batch size smaller. So a more direct way to improve performance is, if you're encountering hotspots, is to just make your max records per Ranger node smaller and play around with that. But in a general sense, let's say there was no hotspot at all in that 1,000 record batch. then you're better off processing all of that in one cycle, so that you have, one match cycle and then one merge cycle, rather than doing 10 match merge cycles of 100 records each. Yeah. So, okay. Is there any strategy for ordering the rules? So we will handle the internal ordering of fields within a rule. So we will always evaluate exact match fields within a fuzzy rule first. Okay. Now, as far as ordering for rules for performance, you can go back to my slide that talks about the rule set optimizations that we do, right? So you might find it good to have exact match fields. So maybe it's better to have a common exact match field that's present in all your rules. Maybe it's better to have a rule containing that exact match field early in your rule set ordering. But I have not investigated. We have not investigated sort of playing around with the optimizations in that manner that much. But that's the way I would think about it. I would think about, how do we do our optimizations, right, in terms of elimination of rules that share common match fields? And you can play around with the ordering to have the biggest impact, to try to eliminate as many rules early as possible. Can the same customer name in 2 different languages match? English name and Chinese. Okay, so we've got 4 minutes left, guys. I encountered this in my first MDM project, actually, and there is a way to do this, and it depends on whether you need to apply AND logic or not. So do you need to say that a customer has to share both names, match on both English and Chinese names or not? If your answer is yes, then you need to have a name field that contains both English and Chinese in the same row. If you have an OR scenario, then you can have a child name table with English, different English and Chinese names. So, but it is possible, sort of our double byte populations can support, sort of the native language. So, China can support sort of Chinese pinyin as well as English, but they can't support multiple native double byte languages. That's just the general rule for our double byte populations. So this is possible with just the China population and with modeling for your scenario. Yeah. 2 minutes left. Vidya has a question around metadata, so have to think about that one. If I have 10 rules for a BO and I update one of the rules in the rule set, what will happen to the match HMRG? And yeah, so Angela is answering that. Okay, if we have daily delta loads, how frequently should we retokenize? So we handle retokenization, the dirties, which is basically the records that have been updated since their last tokenization, for you as part of our match job, right? You don't need to specifically tokenize. But I would be wary of the strip CTAS limit and the strip CTAS ratio that I mentioned on that slide, because that can force a full rebuild of your strip during an incremental daily, which you definitely do not want to have happen, right? So I would pay attention to that slide, pay attention to those limits. They're specified in the back end and see repost table. But yeah. And we're at 1 minute left, and you guys have my email, right? So I'll push my email. You guys can, if there's any kind of lingering questions, you can feel free to email me, or if you have a support project, feel free to, open a GCS case, and we can try to address any of your other questions. Or if you're working with IPS, they're also good, and you can have your IPS person reach out to GCS and myself as well. Okay, good. Thanks, guys.